solve the equations. You can take the square root of both sides, and x is going to equal the square root of 64. Well, 8 times 8 makes 64. And don't forget that square roots actually have two answers. Here, 63 is not a perfect square, so we can just write that x is the plus or minus square root of 63. Complete the remaining 3 problems for your warm-up. This asks you to use the pieces to fill in the large square. So let's see if we move these into this section here. We can kind of line up these pieces in the corners, like so. And we can see that all the parts from a squared plus all the parts from b squared fill in this square for c. What is the Pythagorean theorem? Use the picture or make a sketch if it helps you explain what you know. The Pythagorean theorem says that if we have a right triangle, excuse me, then a pattern exists, or a setup or a relationship exists where a squared, let's see if I can use a little square here, a squared plus the side length for b squared is going to equal the side length for c squared, that longest side, which is called the hypotenuse. So if a right triangle has side lengths shown in the diagram, then a squared plus b squared equals c squared. Our mission: given a right triangle has the side length shown in the diagram, prove that a squared plus b squared equals c squared. It says, let's start with a right triangle. Choose some lengths for a and b. Let's make a, b 4 and b 3. Then if we lock it in, it says, consider the triangle's interior angles. Defend the statement, x plus y plus 90 equals 180. Well, the sum of the angles inside of a triangle all add up to 180 degrees. And we saw this because we called it the triangle angle sum. We saw that this was true in another lesson. So if we add up this 90-degree angle, this degree for x, and the degrees for y, that should come out to 180. Okay, so they've created a square. It says defend the statement. All 4 triangles are congruent. They've rotated this original triangle about point P. The center of rotation, P. What do I know about all those highlighted segments? All of those highlighted segments are A. And all of those are equal to B. The largest square is a square with a side length of A plus B. So this is A plus B. The red plus the blue. The side length is A plus B. This one is also A plus B. So the base and the height of the square is a red with a blue. Okay. What do you know about these highlighted segments? All of the purple segments are equal to C. Can we conclude that the figure in the middle is a square? Why? Well, we know that the four sides are the same, but we don't know about the angles yet, but we can show that the angles are the same. So before we said that we had an angle X and an angle Y and a 90, and that made 180 degrees. Well, those X and Y pieces are also in these triangles here. And right here we have a straight angle. So if X plus Y plus 90 made 180, and this is a 180 also, then X plus Y plus a 90 has to equal 180 there also. So yes, we can say this is a square because a square has four congruent sides and a 90-degree angle. So we can also say the angles are 90 degrees based on a straight angle and the triangle angle sum. So it says earlier you found that X plus Y plus 90 is 180. What does this equation tell you about the interior angles of the figure inside the large square? They're all 90 because it's just a copy of the original triangle. They were all rotations of the original triangle. So this is 90, 90, 90, and 90. X plus Y plus 90 equals 180 from the triangle angle sum. But with a straight angle, it will also equal 180. So that missing piece has to be 90. What is the area of the purple square? Well, we know the side length is C, so C times C would be C squared. C squared. And how do we know? The side length is C, and it is a square. So C times C. The area of the large figure is the same as the combined areas of the purple square and all four triangles. The combined areas of the triangles and the purple square fill in the outer square's area. Takes up all that space. Given a right triangle, or a right triangle has the lengths A, B, and hypotenuse C, and we're going to play. So they've translated those triangles. So there's 1, 2, 3, 4 triangles still, but they've repositioned them. Have the areas of the triangles changed? No. The triangles are the same. They have just been translated. What do you know about these highlighted segments? Those red ones are all equal to A. Is the highlighted figure a square? Yes. The side lengths are the same. And they form right angles. You see a right angle here. This is a straight line with a 90, so this also has to be 90 to equal 180. Same here, this is a 90, creating a 180 straight angle, so that has to be 90 in this corner also. What do we know about those highlighted segments? All blue segments are equal to B. Is the highlighted figure a square? Yes. The four sides are the same. And they have right angles. What is the area of the red square? That is an A times A. So it is equal to A squared. It's a square. You would do base times height for a rectangle. A times A gives you A squared. What is the area of the blue? Well, B times B is equal to B squared. Defend the statement. The area of the large figure is the same as the combined areas of the red square, the blue square, and all four triangles. That is true because the combined space fills up the outer square. For some reason, my reasoning for number 4 isn't popping up, but it says, using what you have reasoned about figures 1 and 2, finish the proof by explaining how the figures prove that a squared plus b squared equals c squared. Well, we know all four triangles are the same, so if we take the outer area, because both of the outer areas are the same, and we pop off those four or remove those four triangles, the space that's left is also the same. We've taken the total area and we've removed the triangles from both. The area that remains would be the same. So then if we rewrote that as a statement, the area of the blue, or the red square plus the area of the blue square, these two areas combined add up to the area of the purple square. It says, let's start with a right triangle, choose some lengths for A and B. Let's use some decimals this time. Defend the statement again. It's a right triangle, so there's a 90-degree angle. If we add up the two angles, X and Y, the sum of the three angles in a triangle always add up to 180 degrees. So if we subtract 90 from both sides, we are left with this equation. We would remove the 90, and 180 minus 90 leaves us with 90. Have the lengths of the segments changed? No, they are rotations of side lengths A and B. If we watch that again, you can see A is rotated out to make those red lines, and then B is rotated as well for all of those blue lines. What is the area of the red square? It is A squared as well, because A times A, base times height. What is the area of the blue square? That is B squared, because it's equal to B times B, the base times the height. Defend the statement. The area of the whole figure is A squared plus B squared. Yes, we have combined the red and blue, but it takes up the same amount of space. So it's just the total of those two squares. What is the length of the figure's base? Well, A plus B. The base would be A plus B. The red and the blue are touching end to end to reach that distance. If the length of the highlighted segment is B, what do you know about the length of the rest of the base? It has to be A. Because if we swap them, it's still the same distance. So now they've created some triangles out of that. It says earlier you found that x plus y plus 90 is 180 using that triangle angle sum. You also found that x plus y is 90. What do these equations tell you about the measure of angle 1, 2, and 3? Well, we know x plus y is 90, so to get a straight line, angle 2 also needs to be 90. The measure of angle 2 have that symbol in here somewhere. There we go. The measure of angle 2 is 90, and the reason that we know that is because it forms a straight angle. Let's see, angle 1. Angle 1, if x is here, this was a square, so we know that x plus 1 made a 90-degree angle. So the measure of angle 1 let me do that. Let's try this. The measure of angle 1 is equal to 90, that's corner, minus x. It's going to be the piece that's left over. Okay, and then for the measure of angle 3, that is going to be 90 minus y for the same type of reasoning. Oh, wait. we can get even more specific. We know that x plus y was 90. So the measure of angle 1 is y, based on that equation. And over here, x plus y was 90, so the measure of angle 3 has to be x. Okay, try moving the triangles to form a square with a side length of c. So we're going to move these guys around. Let's see if we can pop them over here just by translating. Now we have a square with a side length of c. It says defend the statement. After the triangles are moved, the area of the whole figure stays the same. The triangles did not change in size. They were just translated, which maintains or keeps its area. Rigid motions do not change the size of things. It says the pieces look like they fit together nicely, but how do you know they actually line up at the top? Let's see here. It says to answer, defend the statement. The height of the left side and the height of the right side are the same. Well, this was B tall and A tall. This right here is A, and this piece is B. Right here, this was A, and this little chunk was B. You can see here A and B, B and A. Earlier you found 3 unknown angle measures. You also know the angle measures of the right triangles. What do these angle measures tell you about the interior angles of the figure? How do you know? Do these still need to be stacked up here? I'm assuming so. Okay. What do these angle measures tell you about the interior angles of the figure? We knew that x plus y made a 90-degree angle. So this top piece up here, x plus y is 90, x plus y is 90, and x plus y is 90. So we know that the 4 corners of the purple square are, in fact, 90-degree angles. Defend the statement. The shaded portion of the figure is a square with side lengths c. The side lengths are all equal to c, and we just showed that the angles in the corners were 90 degrees, so that makes a square. The area of the shaded portion is c squared. A square with side lengths c would have an area of c times c, which is the same as c squared, or c to the second power. So using what you have reasoned about the 2 figures, finish your proof by explaining how to show a squared plus b squared is c squared. We cut up the red and blue squares and translated to form the purple square. We know that they are all squares by their side lengths and their angles. The area did not change from rigid motions. So the red and blue combined to make the purple area, which means a squared plus b squared is equal to c squared. So this is just a summary of the two proofs we did today, with the 4 triangles rearranged, and then with the 2 squares cut up to create c squared. And you can see that it doesn't matter what size a and b are, those relationships still exist. So we can prove the Pythagorean theorem for any side length. Please make sure your warm-up is finished and any notes that you need to take in your workbook are written down as well.